A very good day to you, learners. Welcome to our geography discussion on geography grade 11, paper 1. Our focus, we are going to focus on discussion of a given set of questions, which are set part of questions for paper 1. And we are going to elaborate on those questions and also try to touch on the content relevant to the questions so that we fully prepare you for the coming end of year examinations. So as usual, we understand that our paper for grade 11 is going to be a full examination paper, which means it's out of 150 marks. And that 150 marks is supposed to be done in 3 hours. So basically, that's the setup of our end of year examination for paper 1, grade geography grade 11. It's a 150 mark paper, which is a full examination, which is to be done in 3 hours. So we check the nature of the areas of coverage that are supposed to be covered by the examinations. We are going to have 2 sections in the examination, and predominantly section A is theory, which comprises of question number 1, which is a question on climate and weather. It takes you back to term 1, where you did basic elements of climate and weather. Then it also has question number 2, which is a question on geomorphology. I think you still understand the geomorphology from term 2, where you covered the different landforms resulting from horizontally layered rocks, inclined rocks, massive igneous rocks. You also covered on mass movements. Right, those are some of the areas of geomorphology for grade 11. Then we have section B. Section B comprises of question number 3, which is a question on geographical skills and techniques, which is our map work question. So it's 60 marks for question 1, 60 marks for question 2 to make 120 marks for section A, then plus 30 marks for section B to make it 150. Right, that's the setup of the paper. We are going to go through the questions and try to figure out the possible responses to the given questions. Right, the first question is section A, climate and weather. It says it's a multiple choice question, number 1.1.1. The seasons occur as a result of what causes seasons? That's the question in simple understanding. For us to have summer and winter, autumn and spring, what is the reason? The reason for us having seasons are created or are generated because of the revolution of the earth. As the earth revolves along its path, the distance from the earth to the sun differs along the elliptical path. As a result, we have differences in weather conditions that give rise to seasons. Right. So it's C, which is a revolution. Then the earth receives more energy than it needs at the equator. As what happens there at the equator, if there is more energy that is received than what is needed, that gives us an energy surplus, which means we have excess heat being received there. We have a positive balance. Right. Then question number 3. The path that the earth travels around the sun is called. The path that the earth travels around the sun, that is called an orbit. That is D. Right, moving on to next question number 1.14. 1.14, it says the summer solstices in the southern hemisphere are characterized by summer solstice. Remember, we have a solstice and an equinox. It's a solstice versus an equinox. So we are looking at a summer solstice. What happens in summer? Remember, a solstice, there is an imbalance in the number of hours during the day and during the night. We have the summer solstice. What happens to the size of the day and what happens to the size of the night when it's summer solstice in the southern hemisphere? That's the question. So whenever we're having a summer solstice, it implies that the day is longer and the night is shorter. So we have long days and short nights. That is typical of a summer solstice. But if it's a winter, the opposite is true. It means we have a short day and long nights. Right. Taking us to number 1.15. What air that is drawn towards a low pressure on the surface of the earth? What happens to warm air? What air that is drawn? We are saying this is our low pressure cell, and this low pressure cell is just over the ground surface. This is our ground. This is our ground surface. What is going to happen if we have a low pressure cell here? It means air is drawn from the surrounding high pressure areas because of pressure gradient. If this area has got high pressure and this area has got also high pressure, it means there is now pressure gradient. The air is driven from high to low pressure through pressure gradient force. And what is going to happen? This air is going to meet in the low pressure and is going to rise. So what is happening here? That's the question. What is happening here to the air? The air is converging. Convergence meaning to say the two air masses are coming together. They are meeting in the low pressure cell. So what happens there is converges. Then what is going to happen in the upper atmosphere is going to be divergence. So it's convergence here, then divergence in the upper atmosphere. So it's convergence for this one, which is our response number C. Right, let's move on to the next question. Number 1.16, it says, the further one moves away from the equator, the more the insolation will. If you're moving away from the equator, remember the equator is the low latitude, which is 0 degrees. Let's say we have 30, we have 60, and we have 90 degrees to the north. And we also have 30, we have 60, and we have 90 degrees to the south. So we are saying this is the equator. What happens to the insolation as you move away to the subtropical, to the subpolar, and to the polar, and also as you move towards the north? If you are increasing your latitude, it means the insolation will, further one moves away from the equator, further one moves away the equator, the more insolation will. The correct response there is insolation will decrease. Moving on to the next question, the amount of insolation that hits the atmosphere depends on the amount of insolation that hits the atmosphere. It depends on what? Amount of insolation that hits the atmosphere will depend on, is it wind? Is it colatitude? Is it Coriolis? Is it the correct response for that matter there? If you are seeing correctly, we can figure out that it must be latitude, like what we were saying here. We are saying if you go to high latitudes, we are moving away from the source of heat. So the equator is the most heated. There is high insolation around this area. And we agreed that if you're moving away, insolation will decrease. So the same implies that you are relating to latitude, which is the distance from the equator, is the one that determines the amount of insolation there. More you move away from the equator, the less the insolation received. One, because of the angle that the sun hits the Earth's surface, and also because of the surface area that is heated by the sun, and also because of the distance that the sun's rays have to travel. They travel through a thick atmosphere where some of the heat is lost through processes like absorption and reflection. Right. We take it to the next point. Question number 1.2. Question number 1.2 is based on a matching column question. We're looking at matching item to solstice. What item matches with a solstice? A solstice, we have talked about it earlier on. We said it's either a winter solstice or a summer where the day is longer than the night, or it's a winter where the days are shorter compared to the nights. So the matching response for a solstice is H, which says the time of the year on which the overhead sun shines on the Tropic of Cancer and the Tropic of Capricorn. I think you can still remember the Tropic of Cancer is at 23.5 degrees to the north, and the Tropic of Capricorn, which cuts across South Africa, is at around 23.5 degrees to the south. So it implies that if the sun is shining over the Tropic of Cancer, it's a summer solstice in the north, where they have a longer day and a shorter night. But when it is over Southern Africa, where it is over the Tropic of Capricorn, 23.5 degrees south, it implies that it will be summer solstice and we are having a longer day and a shorter night, right, in the southern hemisphere. Right, let's move on to the next question. An equinox, we discussed about that. An equinox means equal amount of number of hours during the day and the number of hours during night time. So an equinox, there's a balance in the number of hours during the day and number of hours during the night. So the matching item for an equinox, we find that it matches with the response G, which says the time of the year when the day and night is of equal length, equinox equal. Yeah, the term equal equated to equinox. Right. Move on to the next one. It says Coriolis effect. Coriolis effect is matched with item A. The description A, what does it say? It says the deflection of winds caused by the rotation of the Earth. Right, we are saying Coriolis effect is brought about by the effect of the Earth's rotation. Remember, we have pressure gradient force, which tends to drive air from high pressure going towards low pressure. But the air, remember, is moving over a body which is also moving, such that at the end, we are not going to achieve a positive result as the suggestion of pressure gradient force. That wind is blown from high to low, air is blown from high to low pressure directly. But rather, there is a deflective effect which is caused by the rotation of the Earth, which we call Coriolis effect. And according to the Coriolis effect, the Ferrel's law, we understand the deflective effect is to the left in the southern hemisphere and to the right in the northern hemisphere. Meaning to say, because of Coriolis effect, winds are deflected to the left in the southern hemisphere. They do not achieve a positive result of movement from high pressure to low pressure directly, but rather they twist to the left in the southern hemisphere and they twist to the right in the northern hemisphere. Right, it takes us to the next question, which is question number 1.2.4. Pressure gradient, what is the best description of pressure gradient? We can match pressure gradient here according to the description at item number B, which says is the horizontal movement of air across the isobars from a high pressure to a low pressure. Remember, when air is being driven by pressure gradient force, it cuts across the isobars, meaning to say it will be cutting from high to low pressure at right angles with the isobars. That's the suggestion of pressure gradient. Right, we move on to the next question, which is number 125. It talks about a geostrophic wind. Remember, a geostrophic wind is realized when there is a balance between pressure gradient force and Coriolis effect. When those two come into a state of balance, they produce what we call a geostrophic wind. So we are saying the air is blown into what we feel as the wind because of pressure gradient force, and it cuts across the isobars. But however, when now it's a geostrophic wind, there is a balance between pressure gradient and the deflective effect caused by Coriolis force, such that we have the air blowing parallel to the isobars. So our description of a geostrophic wind, it matches with item F, which says the movement of air parallel to the isobars. Then jet streams, what we call jet streams, those are strong winds which blow in the upper atmosphere. The description for jet streams, it matches with the response number D. Number D says, these are strong winds blowing from the west to the east in the upper atmosphere. Those are jet streams. Circle of eye illuminations, the circle of eye illumination, it matches with item E, which says the boundary between the sunlight and the dark hemisphere. Then lastly, an air mass. An air mass is a large body of air that has got similar characteristics if you are to define it in simple terms. What are the characteristics which are similar? We are saying it's a large body of air that has got uniform characteristics. Those characteristics can be of temperature, which means the temperature is uniform within the whole body. Humidity can also be another feature. Stability can also another feature. So those air masses, they adopt those characteristics from where they originate. If they originate over the warm oceans, we are likely to have them being warm because of the warmer ocean current and also having moisture and also being unstable. If they develop over the cold oceans, they are more likely to be very cold and without moisture and being very stable and more being dense. Right. So that besides the point, air mass is matches with the description at item C, which says a large body of air across the it's a large body of air with the same temperature and humidity. Right. That takes us to the end of question number 1.2. We move on to question number 1.3. Right. I will interpret the synoptic map before we answer the questions. What you must note here, you must check also and be aware of the date of the synoptic map. Our date, we find it here. It is 2022, October 5. Right. And also if we check, we have an anticyclone here, which is a high pressure cell. Our major anticyclones that influence weather conditions or that affect the weather conditions over the South African subtropical, the Southern African subcontinent. We have to the west, this is called the South Atlantic high pressure. And if we check to the east, we have another anticyclone here, which is a high pressure cell. On the east, we have got the South Indian high pressure cell. Right. And if we check over the interior, there's an L here, which suggests that there's low pressure over the interior. This is what we call a thermal low pressure cell over the interior. Right. And also we are seeing this weather system here. This weather system is, the whole system is called a mid-latitude cyclone. It's a mid-latitude cyclone, the MLC. Right, and that weather system, which we call the mid-latitude cyclone, is comprised of two fronts. On one side, this one with a blue is called the cold front. Those triangular symbols that are along the line, they represent a cold front. And on this side, the red one, the red indicated, which is like a semicircle, is called the warm front. They are both part of the weather system of the mid-latitude cyclone. And also, what else do we need to note? I think those are the basic elements that we need to note over that synoptic map. So let's try to answer the questions in as quickly as possible. The pressure gradient at A, is it steep or gentle? Let's check at A. We are seeing this line drawn here at A. Let us try to analyze the isobars which are crossing along the line at A. If we see our isobars as close to each other like this, it implies that it's a steep gradient. And a steep gradient, it gives us strong winds. The winds which will be blowing between those two places from a high pressure to a low pressure, they will be very strong because the gradient is steep. But where we see our isobars spaced apart, this is what we call a general gradient. And general gradient, it results in weaker winds. Right. So if we are to interpret here, we can safely say it's a steep gradient because isobars are close together. Then identify the high pressure cell at B. I think we have already indicated that this is what we call the South Atlantic high pressure cell. Right. Then in which direction does the air circulate around the high pressure cell identified? Right. What you must note is when we are in the southern hemisphere, we are making special reference to the southern hemisphere. When we have a high pressure cell, air, when it's circulating out of the high pressure cell, it circulates in an anti-clockwise direction out of the high pressure cell. And when you have a low pressure cell in the southern hemisphere, the air feeds into the low in a clockwise direction, like this. So it's anti-clockwise out of the high pressure cell in the southern hemisphere and clockwise in to the low pressure, into the center of the low pressure cell in the southern hemisphere. For the northern hemisphere, it's the opposite. The opposite is true for the high and for the low pressure cell. So here our correct response is anti in an anti-clockwise direction. That's the circulation. Right, draw the weather station at Howe Island and that indicates the following weather conditions. Right, cloud cover, we indicate it in the circle. We draw a circle like this. When I'm drawing this circle here, we shade the relative amount of cloud cover inside the circle as a fraction of 8. You must always note that our cloud cover, we present it as a fraction of 8, which is what we also call the octants. Right, so we are saying cloud cover is presented as a fraction of 8, which means if half of the sky is shaded, it's going to be half, which is 4/8 or 4 octants. Right, so here we are told that it's overcast. When it's overcast, it means the whole sky is covered. So we are supposed to shade the whole circle. Everything must be shaded inside the circle to suggest that the sky is fully covered. That is cloud cover. We present it inside the circle here. Then wind direction. With wind direction, we are supposed to figure it using an arm stretching from the circle to the given direction where the wind is coming from. Remember always that when you are drawing your weather station, or when you are dealing with aspects of direction in geography, your west is always to the left and your east to the right. Then your north always to the top and your south to the bottom. So southwest, we are saying the wind is in this direction. That is how we determine wind direction. We point it by that arm stretching from the circle to the given direction. Then we have air temperature and we have dew point temperature. Our temperature values are presented by the side of the circle with the maximum or air temperature on top, which is 13. And we have our minimum temperature, which is 11. So that is basically how we portray the weather station. We know that the circle presents cloud cover. This arm weight points, it shows us wind direction. If there were some feathers at the end, they will be used for wind speed in knots. Then these two figures will be representing temperature in the form of air temperature, which is the bigger value, and the smaller value representing dew point temperature. And basically, if there's precipitation, it will be shown in different, using different symbols for thunderstorms, for rain, for snow, for drizzle, all those forms of precipitation. If they are there, they will also be presented using the different conventional symbols which are used for the different weather elements. Right. Let's go to the next question. It says, refer to weather phenomenon at F. Name the front of the weather phenomenon at F. At F, we talked about that. We said it's a mid-latitude cyclone, and this one here at F, which is labeled, name the front of the weather phenomenon at F. The front, we've talked about the two fronts that we find, and at F, that is a cold front. Right, in general, in which general direction does this weather phenomenon move? This weather phenomenon of mid-latitude cyclones, they move from west to east. Move from west to east, or generally we can say they move eastwards. That's the movement direction. Then it says, name the planetary wind belt that steers this weather phenomenon in the direction mentioned in question 135. Right, let me just briefly take you back to the global air circulation model and also refer you to the planetary winds. Right, if we have this As our globe, though it's not very spherical, we have the equator at 0. We have our subtropical at 30 to the south, and we have our subpolar at 60 degrees to, or rather, let me just make a clear illustration so that it becomes very clear for the interest of those who might also want to use the information. Right. We are saying, we are referring back to the global model of global air circulation. We want to show the belt, the planet of planetary winds responsible for the drive of the mid-latitude cyclone. Right. We are saying on the globe, we are having this as our globe, right? So we are saying midpoint at 0 degrees is the equator, and at around 30 degrees to the north, we have the subtropical high pressure, and around 60 degrees to the north, we have the subpolar, and at 90 degrees to the north, we have the polar region. Then the same pressure belts are also realized going to the south. It's 30 degrees to the south around here. At 60, we have another pressure belt, and at 90, we have the 90 degrees to the south. Right. So in terms of pressure distributions, this is a high pressure, which is called the polar high pressure, and the polar again to the north, which is a high pressure. Then again, from the equator, this is a low pressure because of intense heating. There's low pressure here. This is a low pressure belt, and this is a high pressure belt, which is caused by sinking air. So around this region is called the subtropical region. Then we have the subpolar. It's a low pressure belt, which is caused by relative deflective effect. So this one is the subpolar region. Then the polar is a high pressure because of excessive heating. And the same distribution happens to the south. We have subtropical to the south, and we have subpolar to the south. Then we have the polar. So because of high pressure and low pressure distributions here, there's high pressure, there's low pressure, there's high pressure here. Air is supposed to move from high going to low pressure, but we said there is Coriolis effect is going to deflect the winds in a given direction. And what did we say about deflective effect? Instead of the wind going, this is our west, this is our east. Instead of the wind going from the air coming from high to low directly, is going to twist to the left in the southern hemisphere, which means our winds are going to blow in that direction. They are going to bend towards the left. And in the northern hemisphere, they are going to bend to the right because of Coriolis effect, such that we have the winds in that pattern there. So this is the belt of planetary winds around the tropical region. Then from high to low again, the air masses, they do not go straight from high to low, but rather they have to turn to the right, which means they twist to the right like this. And again, from high north, they are supposed to come to the low pressure, but they will twist to the right in the north. Then this, what happens in the south is from high to low pressure, they are supposed to slightly twist to the left because of the deflective effect. So they will twist to the left. And from high to low, again to the left. So at the end, these are our planetary belts. This belt here is a belt of what is called the polar easterlies, in the sense that the winds, they originate from the polar region and they are coming from the east going to the west. So it's polar easterlies, and this belt is a belt of what we call westerlies. Westerlies in the sense that the wind in this belt, they blow from west going to east. And then in this region, these winds are coming from the east going to the west. It's a belt of tropical easterlies. So the same happens. We have the other belt of westerlies here. At this belt between 30 and 60. Then we have another belt of polar easterlies. So those are our planetary belts. So our mid-latitude cyclones, they occur in this region here. They occur not in this region, rather it's to the, they occur in the region of the westerlies here. We find our mid-latitude cyclones happening in this belt here to the south. So they are driven by these winds here, the westerlies. And also, they are driven by the same in that particular belt in the north, such that we have our winds from the west to the east, like what we mentioned, that they move easterly or from west to east. Right. That was the idea. We're just highlighting on the idea of the tropical, the mid-latitude cyclones, what steers them, what makes them move in that direction. So it's because of them being steered in within the belt of the westerly wind belt. So it's the westerly wind belt. Right, taking out the next question, it says, discuss how the weather conditions will change when this weather phenomenon at F moves past Cape Town. When it moves past Cape Town, we are looking at the coming of the cold front. How is it going to affect weather conditions? The cold front, remember, it brings in cold conditions. So we are going to experience a drop in temperature. Temperature is going to decline, it's going to decrease. And also we are going to have gust winds, strong winds associated with pressure gradient. Then you're also going to have other aspects of a dense cloud cover because of excess condensation. The cloud cover is going to be dense. We have the formation of cumulonimbus clouds there. And also we can go look at other aspects of talked about the strong winds, we talked about the drop in temperature, we talked about dense cloud cover. Yes, because of excessive condensation that is going to happen. So basically, those are the ideas that those are the weather conditions which are likely to be brought by the coming in of a cold front over Cape Town. Right. Then we move on to the next question. Define the term drought. We are talking of a drought situation. We are saying it's a period. It's a period of below average rainfall. A period of below average rainfall. Whenever we experience rainfall below the expected average, then it means we are having a drought situation. Then some causes of droughts. What is likely to be causing droughts? Right. We look at the cause of droughts. We can talk of a drop in amount of moisture in the air. If the amount of moisture that is contained in the air drops, most likely we are less likely to have condensation taking place, and that is going to bring in drought conditions. Then you can also look at the changes in ocean atmosphere. Changes in the ocean atmospheric conditions. For example, we talk of the issue of El Nino and La Nina. Then we can also look at the shift in wind patterns. The winds that used to bring in moisture laden air, if they change direction, then it means also the place is going to have high chances of drought. Then we can also look at locations of the high pressure cell. Location in high pressure cells. For example, placed in South Africa, they are mainly in the subtropical high pressure cell, where we have problems of sinking air. And sinking air, remember, it creates clear cloudless conditions that are less likely to result in any form of precipitation. So we have drought conditions because we are located in the zone of high pressure cells where the air is sinking. Right. Those are some of the aspects that we can highlight as the causes of drought. Then it says, why are developing countries more vulnerable or at risk or to drought than developing countries? Right. The problem with developing countries, what is the typical problem that make developing countries vulnerable? Right. We can look at aspects like In developing countries, many people are living in rural areas and they depend on land for their livelihood. Or we can look at being a subsistence. Let me just find somewhere to write clearly. We're looking at question number 1.4.3. I'll present it here. Right, we're looking at question number 1.4.3. Right, we are looking at a situation whereby we are saying in developing countries, most people, they live in rural areas and they depend on the land for their livelihoods. They are subsistence farmers. So for that sake, this kind of farming is very vulnerable to drought conditions. If there is limited rainfall, these farmers don't have any way of harvesting water. They don't have any irrigations. They just rely on rainwater. And as a result, they are very prone and much prone to the effects of drought for that reason, that they don't have a cover. Then also a limited variety of crops. Sometimes we need to diversify our crops so that we absorb the risk of drought by growing also drought-resistant crops in the mix, such that when the other crops fail, we also have a harvest from the other crops. But in this instance, if you are growing predominantly one type of crop and that crop is not drought-resistant, then the implication is whenever there's a drought, we are more vulnerable to be having challenges with the drought conditions. Then you can also look at limited food storage facilities. Storage facilities. We need storage facilities in case we harvest more than what we need to consume. We need to safe keep the food reserves and use them in case when we have a challenge, like during a drought situation when crops have failed. And also we can look at aspects like little insurance, against drought. It's another problem. The farmers have got little insurance. They are not insured against drought, which means if their crops fail, and they are most likely to be affected because they don't have any cover-up plan to sustain them during the time of failure of their main source of sustenance, such that at the end, they will sustain without any challenges. Right. You can also look at other aspects like limited financial capacity to import. They also need to import in case there's a drought, but however, there's limitation of financial resources for importation to buy from other countries. Right, we go on to the next part, which was question number 1.4.3. We need to move on to the next question. We have talked about this as cover-up measures. Why developing countries are the ones who are more vulnerable to the problem of drought. But however, you can also note some other responses. You can also come out with other relative responses to the question. It's not only that we are saying these are the right responses, there can be other responses that we did not mention. In a paragraph of basically 8 lines, briefly discuss sustainable measures that could be implemented to manage droughts effectively. We want to look at sustainable measures that could be implemented to manage drought. Right. So it's number 144. Let's say it's managing drought, strategies of managing drought. This question number 1.4.4. Right. Managing droughts and drought conditions. What can we do as a way of managing droughts? Right. We can talk of building dams to store water. If we build dams, it means they act as reservoirs to keep water. We can use it in times of droughts, such that crops can be irrigated and also livestock would find drinking water. Right, we can also look at other aspects like cloud seeding. We try to use artificial methods of seeding clouds so that we can have rainfall. We can look at desalination of ocean water or seawater. Desalination, we are saying we are removing salts. Remember, seawater is salty. So we need to find ways of desalinating it so that it becomes potable, it becomes drinkable and usable. So we need to desalinate, remove the salts which make the seawater very salty and which makes it unsuitable for use. Right, then we can also look at recycling water. Recycling water, we can recycle water so that we save it. And we can also look at rainwater harvesting. Rainwater harvesting from rooftops. We can use gutters to harvest rainwater into storage tanks, into JoJo tanks that we can use when we are having a difficulty. Then you can also look at other aspects like introducing water restrictions, try and control the amount of water which is being used at any particular point. Then you can also look at other things like education, which is a very vital tool. Education or awareness campaigns to educate people on the need to save water so that when we have a drought situation, we might be prepared for it and we might be having some reserves of water that we might use during a difficult situation. Right, with that being said and done, I think we've done justice to the first to this question here on droughts. We've done justice to the question on droughts. We need to move on to the other part of the question and try to figure out how we can answer that particular question. We are taking it to question number 1.5. Question number 1.5 is based on the monsoon wind. Right, the monsoon, it says define the term monsoon. Right, monsoon, we are looking at a seasonal wind. It's a seasonal wind that mainly occur mainly in tropical regions. Right, basically when I'm talking of a monsoon winds, we are looking at, sometimes we define it as the seasonal reversal of winds, and the associated weather. The winds reverse direction of movement according to changes in seasons. Like if you are seeing here, this wind is going in this direction to the north, but in some season, it's going to the south. It is reversing its movement direction. It's a seasonal wind, which means it blows. It's a regional wind, rather, which is specific to a given region. And we say the region is mainly in the tropical region. And how does it operate in relation to seasons? The wind changes direction according to changes in seasons. At one particular season, it's going to the north, and in another season, it's going to the south. That is typical of a monsoon wind. What does ITCZ stand for? ITCZ stands for Intertropical Convergence Zone. That is the ITCZ, the Intertropical Convergence Zone. Right. Why does the wind at A change direction from southeast to southwest? At A, you are seeing it was going to south, it was going to southeast to southwest. Why does the wind at A change direction from southeast to southwest? Right, why does the wind change direction in that given way? Like we are seeing here, it's changing direction. Why is that happening? That's the question. We need to account for the change in direction for that particular wind. The reason here, the main reason that we must highlight is the change in direction is brought about by Coriolis effect. Coriolis effect, it produces a deflective effect. The wind is deflected because of Coriolis effect. We are saying the wind is moving from high to low pressure, is moving across the equator to the ITCZ where there's low pressure around the ITCZ here. But the general pressure gradient is driving the wind in this direction. But however, because of Coriolis force, the wind is slightly turning to that direction. It's slightly turning to the right. Why? Because we are in the northern hemisphere here. The deflective effect, it happens in the right side. Remember these typical weather conditions, we experience them over India. And we are talking of the Himalayas there. We are in the northern hemisphere. We are talking of the Bay of Bengal. We are in the northern hemisphere there. So what is happening there is because of the deflective effect of Coriolis force, the winds tend to change a direction and twist in that direction. They are deflected by Coriolis effect. Right. Account for the difference in the position of the ITCZ during winter and summer as illustrated by these diagrams above. Account for, right. So why does the ITCZ change position? It's here during summer, and in winter, it's here. Our equator, we can see it's here, which is our 0 degrees. So we are saying account for the difference of the ITCZ. Right, the ITCZ, we are saying the intertropical convergence zone, the ITCZ lies directly at a perpendicular angle with the sun's overhead position, which means it's an area of low pressure which is created by the intensive heating caused by the sun's overhead direct position with the ground surface. So what happens is, why does the ITZ, why is it in the north in summer? Right, we are saying here, this is not the hemisphere summer. The sun is to the north. So our argument here, we are saying the ITZ moves northwards, causing intensive heating and the convergence of tropical winds, which result in massive evaporation in the north. So it moves the north. In summer, because that is where the sun is directly hitting. The sun directly hits over the Tropic of Cancer when it's summer in the northern hemisphere. So the ITCZ also shifted to the north because that is where the overhead position of the sun is. And in winter, it shifts to the south. Why? The sun's overhead position is over the Tropic of Capricorn, which winter. So you must know in the sense, in the geographical sense of the northern hemisphere. That is why we are saying it's summer when the ITCZ is to the north. If this was southern hemisphere, it was going to be opposite. Because when the ITCZ is to the north, it means high temperatures are in the north, and that will be winter in the southern hemisphere. But in this instance, our illustration is referring to the northern hemisphere. Don't confuse yourself. We are referring to the northern hemisphere. That is why we are saying when the sun is over the Tropic of Cancer, it's summer. But you know well that when it's southern hemisphere, it is going to be winter. So it's the opposite. When it's summer in the northern hemisphere, it's winter in the southern. June is a summer month in the northern hemisphere, while it's a winter month in the southern hemisphere. December is a summer month in the southern hemisphere, while it's a winter month in the northern hemisphere, because we share the same sun. If it's to the south, it means it's far away from the north. If it's in the north, it means it's far away from the south. Right, I think that is explained. Evaluate how heavy rain associated with summer monsoon can be a blessing and a curse on human activities in India. How are Indians blessed and how are they cursed by the monsoon, by summer monsoon? Right, we understand that during the summer monsoon, it brings in heavy rainfall. So we are saying, how is rainfall, heavy rainfall, a blessing? And how is it a curse to the people of India? A blessing, we are saying the positive. How is heavy rainfall a positive development or a positive phenomenon for the people of India? We are saying it's a blessing in the sense that it fills up Water bodies, the different water bodies are filled up and people have got water for use. We can also look at it boosts up agricultural productivity because crops have got enough moisture for sustenance. We can also look at availability of water for livestock. It's a blessing. We can talk of other aspects of the benefits of the rainfall. We can look at it as water for hydroelectric generation, hydroelectricity generation. They have sufficient water for such. So there are many benefits here of having water. You can look at water for domestic purposes. Water for industrial use is readily available because of the heavy rainfall, which is feature of the summer monsoon. But however, it's a case, it's a negative implication. Why is it negative? Talk about flooding. The implication of flooding. How does flooding affect? Flooding poses a negative impact. It poses a challenge on the people of India. It can destroy properties. People can lose their properties, or even you can look at the problem of drowning. People can drown and die from flooding. We also have other impacts like infrastructure damage. You can look at the different types of infrastructure which can be damaged. For example, bridges, they can be damaged. Look at things like land movement, mass movements like mudslides. It can also happen. It can also facilitate other forms of mass movement like the rock falls can be facilitated. The landslides can also happen because of heavy rainfall. You can look at the spread of waterborne diseases. They can easily spread with heavy rainfall. So basically, that is how you look at it. You look at it from the positive side of heavy rainfall and you look at it from the negative side of heavy rainfall. So we must address either side. Do not focus on one side. Remember, it's a 6-mark question, either 2 on positive and 1 on negative, or 2 on negative and 1 on the positive. Right. That takes us to the end of our climate question. We are moving on to geomorphology. Geomorphology, we are having that illustration. That is an illustration of landforms resulting from inclined rock strata or tilted rocks. Right. I think you still remember we talked about the inclined rocks where we looked at the different landforms which differ according to the angle of inclination. There's the Oxberg, there's the homoclinal ridge, there is all those landforms. I think you still remember them. We don't need to go to them. We just need to look at the questions. Right, those two, we are seeing the difference here is on the steepness. This is a gently sloping resistant strata, and this is a steeper sloping deep slope. And then we have the scarp slope on either side. Right, so let's check. It has the steepest. You are supposed to answer those questions based on the two illustrations, A or B. Yes, the steepest scarp and deep slope. Steepest scarp and deep slope. The scarp slope is here and the deep slope is here. The steepest is B. Then, yes, the most suitable locations for dams. Dams are most suitable where we have steeper, hard and resistant rock. We can have them at B. The deep slope can be utilized for farming. The deep slope here, where it's gentle, that is where we can use it for farming. It's A. Then composed of steeply tilted rocks. Steeply tilted, steep tilted is B. Formed by gently tilting rocks. Gently tilting is A. The scarp slope is more than 45. I think you can see there it's B. Then number 7, it says the steep scarp has a steep scarp slope and a gentle deep slope. You can see that the scarp slope is steep here, but the deep slope is gentle. That is A. And then the last one, the scarp slope is more than 10 to 25. That is A again. Right, that is question number 2.1. We move on to question 2.2. Question 2.2 is basically referring to slope elements, the elements of a slope, starting from the uppermost part of the slope where we find the crest of the slope, going to the cliff or the free face and going to the talus and the nick point, which is a sudden drop in gradient on a slope, and we go back down to the pavement. Right, without wasting time, let's look at the questions and refer to those aspects of slope elements. The slope element with the least soil coverage, least soil is on the cliff or the free face. Why we are saying so, if you check here, it's almost vertical. There cannot be soil accumulating on that vertical slope. 2.22, it says the slope element where construction of buildings and infrastructure is easier. We can only do it here on the pavement. Right, then the next question is saying the dominant geomorphological process on this element is rock force. The rocks, they fall here where it's vertical. It happens on the cliff or the free face. The feature that indicates the sudden change in the profile from one element to another, that is a nick point here. The slope angle is changing. So that is a nick point. Right, the next question is saying the slope element that has a convex shape. Remember the difference between convex and concave. This is a concave, this is a convex. Right, so we want some element with a convex, where we find a convex slope. A convex, we find it on the crest or the free face. The crest on top there before the cliff. Then the slope element with a constant gradient. Constant gradient is the talus. And then lastly, the slope element where the accumulation of weathered material is impossible. Impossible on the cliff is vertical or the free face. Right, we are done with that question. We'll move on to the next question. The next question is based on the landforms of the Karoo, the features of the Karoo landscape. It refers to those different features. Let's just briefly discuss them before we answer the questions. Right, if we see this one here, element number 1, this is a flat high-lying area, which is the plateau. And the plateau is reduced because of the process of backwesting. If it is reduced, then it is reduced into some other landform that we can also refer to in this instance here as the mesa. The mesa, and we have what we call a butt. What's the difference between a mesa and a butt? A mesa is wider than its height. It's wider than its height. Then this one is narrower compared to its height. So what are we saying? If you check the upper part here, it's wider compared to the height here. That's a mesa. It has a wider top, which is compared to when you're comparing to the height. But this one, the top part is narrower compared to the height. Though the height is the same of this mesa and the butt, but the butt is smaller on top. But compared to the height is bigger than there. That's the distinction between those two. And also mind, this is what we call the cape rock. The hard and resistant rock on top of this landform is called the cape rock, is the one that sustains the softer rocks underneath. Because there's a protective layer on top, the softer rocks are protected from being eroded. That is why they sustain. But however, with time and with the process of backwesting, with the process of scalp retreat, the cape rock will gradually be weathered and eroded. And as it is eroded, it ultimately results in the reduction of the size of the whole landscape, because the protective layer, if it's broken and is removed, then the landform keeps on declining in terms of its width until it becomes this one without a cape rock. This is called a conical hill. So those are typical features of the landscape of the Karoo. Right, let's answer the questions. Are these Karoo landscapes associated with horizontal or inclined? They are typical landforms of horizontal strata, right? Identify the Karoo landscape number 2 and 4. We have talked about that. Number 2 is a mesa. Number 4 is a conical hill. Describe the formation of the Karoo landscape labeled 4. Labeled 4, you explain this from the formation of these landforms here. What you need to explain here is the fact that there is no more Cape Rock here. The conical hill develops from a butt along the line of development. The butt, the Cape Rock is eroded. Cape Rock is weathered and eroded. Is eroded away. So from the butt here, if the Cape Rock is eroded away, then it becomes a cone because it's no longer has a protective flat surface on top. It forms a cone because of the loss of the protective layer from the top. So you explain that the butt, from the butt, that is where the conical hill develops. It is because of the weathering and the erosion of the Cape Rock. When the Cape Rock is finally detached or is removed completely from supporting the softer rocks, then the softer rocks will gradually be eroded to form a conical hill. Right. Then define the term scarp retreat. We are talking of scarp retreat. I'll use this illustration here. Right. Let's say this is our mesa. This is our Cape Rock on top of the mesa. And this is our landform. Right. This is a hardened resistant rock on top, which is covering up softer rocks underneath. What is going to happen with scarp retreat? We are saying this slope is going to make to retreat like this, to move like this. So it means in one cycle of erosion, the landform is now here. It's reducing in size because the Cape Rock has been weathered and eroded. Also, it means the softer rocks are going to be eroded. But what you are seeing here is the slope angle is not changing. So the landform, it becomes gradually smaller and smaller because of the retreat. Like it comes to cycle 3. If this is 1 and this is 2, it means our landform is now here. It's no longer a mesa. It's now a butt at cycle 2, cycle 1 there. It's reducing in size, which means the remaining Cape Rock is only this, which is now narrower compared to the height of the landform. So when I'm describing scarp retreat, describe it in the sense that you talk about parallel retreat of the slope. It's retreating in parallel, meaning to say this line is parallel to this one, meaning to say the slope angle is the same. And as a result, it is caused by lateral erosion and the angle does not change. So talk of lateral erosion, which is sideways erosion. Lateral erosion is responsible for parallel retreat of the slope. And as a result, the slope angle does not change. The landscape maintains its shape, but however, the size is reduced because the slope will be retreating. It will be moving inwards. Right. Then it says, describe the similarities and differences between landform 1 and 3. What are the similarities between 1 and 3? Let's just highlight them there. Right. If you check, 1 is the plateau and 3 is a but how are those two similar and how are those two different? Right. We'll start with the part of similarities. If you check this one here, it has a protective rock layer, which is the Cape Rock. So its similarity, there has a Cape Rock, and also this, if you check, it also has its Cape Rock. So they are similar in the sense that a plateau has got a Cape Rock, and also the but also has a Cape Rock. But we look at the differences. This one here is larger. It's got a larger Cape Rock. If you can see, it's extending as a flat lying area. This one has got a smaller Cape Rock. So basically, those are the similarities and the differences there between those two. Right. Taking us to the next question, discuss why these landforms are not suitable for human activities. Why is the Karoo landscape not suitable for human activities? By referring to human activities, we are looking at the major activities sustaining human life. like agriculture, like settlement, infrastructure development. Why is it impossible? Why are these landforms not suitable for human activities? Why is the Karoo region of South Africa sparsely populated? Why don't people prefer staying in those areas? One, the area is too dry. The area is too dry for agriculture. We cannot sustain agriculture in that area because the area is too dry. There is very limited rainfall there. And also we can give the other argument of it being too steep. Those features, they produce steep slopes. Too steep for settlement, we cannot effectively settle. It's very difficult to do construction there. And also it's difficult to construct or to develop infrastructure. If you want to construct a railway or a road or communication infrastructure, that's very difficult because of the nature of the terrain. And also, we can argue that because of the fact that the area has got thin soils, because of the slopes, the soils are not fully developed. So we cannot sustain agriculture for those reasons. Those are some of the reasons that you can highlight. We are not limiting to only those. There are other also reasons that you might highlight. Like it's also difficult to extract water, for example, in those areas. It's difficult to extract water. In those steep sloping areas, you find water deep down in the valley. And if you are settling on the upper valley, on the upper part of the valley, it's very difficult for you to access and extract water for that reason. Right, we look at question number 2.4. Question number 2.4 is referring to the sketch A and B, or intrusive landforms. Right, we're going to answer the question without wasting much of the time that we have. Right, it says label X and Y. If you check X here, it is a mushroom shaped, which is a lacolith. If it was saucer shaped, it was going to be a lapolith. Remember the difference between a lacolith and a lapolith. In this instance, we are saying a lacolith and then a lapolith like that. So this is laco, this is lapo. So a mushroom shaped is a lacolith, so it's our lacolith here. And this one is cutting across the bedding plane. This is what we call a dike. It cuts across, like you are seeing here, it is cutting across bedding planes. It's cutting across rock layers. Right. Explain the difference and similarities between landform X and Z. Z is this bigger landform at the bottom, and our X, you can see, is this lacolith here. So we want to try and figure out the differences between those two, a lacolith, and comparing it to a dike. So a lacolith, basically, we can say this one. Let me use here. When we're comparing a lacolith, we are saying how does it form? A lacolith basically forms when magma. It forms when magma squeezes between rock layers. And what is going to happen? And push it upwards. That's how a lacolith forms. It forms as a result of magma squeezing between rock layers, and it manages to force the upper rock upwards, creating a mushroom shape. And what about the bigger one, which is the batholith? How does it form? The batholith, we can say, is formed deep under the surface. It forms at very great depth under the surface, unlike the lacolith, which forms by squeezing in within rock layers. And also, we're looking in terms of the size, you can say this is the largest intrusive landform. So we are saying In terms of this comparison of these two, let us refer back to them and see how they look like and how we are referring to the explanation of those two. Why we are saying the batholith is formed deep underground surface and is also the largest landform, and also why are we giving that justification of it being the largest of all intrusive. Right. So basically, by looking at that, you can see that the distinction between these two is based on this one. You see the size is basically the biggest of all intrusive. This one is a very big compared to this one here in terms of size. So a laccolith is relatively smaller compared to the batholith, which is big. So in terms of comparison of size, the difference is that this one is relatively smaller and it forms in between bedding planes. It's formed between rock layers. Right? This one is big and is forming at the bottom. You see the distinction there. But if you can check the similarities, we are saying both of them, they are intrusive features. This one is an intrusive, which means it forms inside. And also this one is an intrusive feature. So basically, if you're highlighting the similarities, talk of them being both forming from the solidifying magma inside the Earth's crust. And they are intrusive features. That is how they are similar to each other. But in terms of their differences, we are saying they are different in terms of the size. The batholith is very big. It's the biggest of all intrusive features. And the laccolith is relatively smaller. And also the batholith forms at the bottom. It forms actually at the bottom. And the laccolith, it forms in between the rock layers. Right. Then it says, refer to photograph B. Is photo B a dome-shaped landform? South African example of a photo B, where do we find such an example of this typical landform, a dome-shaped? Is in Paarl, where we have the Paarlberg. Is photograph B an example of intrusive or extrusive igneous landforms? We are saying, is it intrusive or is extrusive? In this instance, we are saying it's now an extrusive in the sense that it's now exposed. It's now extrusive. Why? Give a reason. Initially, the landform formed from underground. Initially, in most instances, for those ones to be exposed, like the granite domes, they start from intrusive features which are exposed because of erosional processes. So what usually happens is, with such landforms, they are exposed to the surface because of some cycles of erosion. So we justify the fact that it's exposed now. It's exposed to the surface. Initially, it was an intrusive formed, or it cooled underground, but later on exposed to the surface because of cycles of erosion. Right. Name the type of weathering that occurs on this dome. The granitic domes, they experience physical weathering, or we can call it mechanical. And the specific type of physical weathering that happens on those ones is exfoliation. Exfoliation. We are referring to that type of weathering whereby the outer layers of the rock peel off because of series of expansion and contraction. During the day, the outer layers of the rock are heated, they expand, and during the night, they are cooled and they contract. That alternating heating and cooling results in the outer layers developing cracks, and at the end, they peel off. That's the process of exfoliation. Right, taking it to the last question of question 2.4, it says, explain how this landform in B has developed. Explain how this landform in B has developed. Basically, the description is related to what we have discussed on. Right, we are saying this landform, how it forms. The granitic domes, they form as a result of mass magma solidifying underground. Mass magma, it actually forces itself underground and cools down. And then the overlying rocks, being weaker rocks, the overlying rocks are eroded. They are eroded through cycles of erosion, and the hard and resistant rock comes out in the form of that granitic dome or those dome-shaped landscapes. Because of the action of rivers, the rivers, they tend to erode the material which is covering up those features, and they get exposed. And now as they are exposed, the process of exfoliation happens, resulting in them having a smoother surface which is rounded. It is shaped now because of the process of exfoliation as they are exposed to heating and cooling on the outer surface. Right, let's look at question 2.5. It talks about Mpumalanga road closure updates following flooding result to rockfall and landslides. It's a question on mass movements. Right, let's look at the questions. We are not going to go through the text. Name one physical factor mentioned in the extract that contributed to this type of mass movement. Name one physical factor. Right, it says several roads across Mpumalanga remain closed due to having collapsed or being hit by rockfalls due to heavy downpours. That's the physical factor. Heavy downpours, or we can say because of heavy rain. Right? What are the factors that determine the speed of mass movement? The speed of mass movement, whether the material moves faster or moves slower, it depends on factors like, number one, the gradient of the slope. Some mass movements are faster because there is steep gradient. For example, rock falls from a steep sloping, they are very fast because of the nature of the gradient. While you can talk of also features like, for example, landslides, or you talk of soil creep, they happen at a very gradual pace. Soil creep is even invisible to the eye itself, but rather it happens over a longer period of time in a gradual way. So gradient of the slope, where the slope is steep, the movement is faster. Where the gradient is gentle, the movement is most likely to be slower. And also look at vegetation on the slope, amount of vegetation on the slope. If there's vegetation, it stabilizes the slope and the movement will be slower. But if there's no vegetation, it's likely that the movement would be slow, would be fast. The amount of moisture in the soil. Amount of moisture in the soil also determines if there's more moisture, the movement is likely to be faster because moisture provides a lubricant for the movement of the material. Then also you can look at the structure of the underlying rock. Where we have underlying rocks which are solid and unbroken, the movement is faster. But where we have underlying rocks which are fractured, we likely have to have a slower movement. Right, those are some of the factors that we can mention. Briefly explain the negative impact of rock falls on the physical environment. On the physical environment, we are looking at the natural environment. How do rock falls impact on the natural environment? We look at things like the damage to trees. As the rocks are falling, the impact on the natural environment, we are looking at rock falls on natural environment. How do rock falls impact on the natural environment? We look at aspects like damage to trees, and natural vegetation. As the rocks are falling, they cause damage to trees. They can destroy trees along the way and also destroy natural vegetation. Then you can also look at the other impacts like the rock falls will kill wild animals. If the rock falls find on their way wild animals, they are going to kill them as they go down. Also, the rock falls, they can block rivers, resulting in temporary damming, which can cause flooding on the environment. We are looking at temporary damming here because of the rocks that would have fallen. It can also result in loss of fertile soil as it covers the soil. The rocks that would have fallen, they will cover the soil and will reduce the amount of fertile soil. And also, they promote soil erosion. As the rocks fall along, they can create some pathways that will likely to be followed by running water, and those pathways will gradually develop into gullies, which is a factor of soil erosion. Right, that is some of the ideas. Those are some of the ideas that you can use to answer that question. Let's look at the other question. The other question is saying, in a paragraph of approximately 8 lines, explain the precautionary measures that municipalities of Mpumalanga can implement to minimize the impact of rock falls in the region. What can the municipality do to minimize the impact of rock falls? Right, so we are saying minimizing rock falls. The municipality, what can they do to minimize rock falls? What they can do here, they can use netting or caging. That will contain the falling rock to keep the material intact. Or they can use bolts and nuts to stabilize the rocks. They can use bolts and nuts to stabilize the rocks. And also, they can also try to introduce vegetation, increase vegetation. Vegetation cover on slopes to bind the soil. Right, it can also help reduce. And you can look at the municipalities also can build what you call rock walls at the base of slopes. If they build rock walls, it means those rock walls are going to contain the rocks before they reach into infrastructure or into humans, such that there is limited damage. So you can you can also look at the issue of spraying cement. You can spray cement on slope sides. To stabilize the rocks. Right, those are some of the measures that can be implemented by the municipality to try and reduce the impact of rock falls. Right, that takes us to the end of our geomorphology question out of 60. So the total for our theory section is out of 120 marks. Now we are going to look at geographical skills and techniques. This question is based on the given map of Greece. And in this discussion, we are not going to use the map, but rather I'm going to guide you through the basic skills that you're going to employ in answering those questions, and the basic techniques that you need to have at your disposal that are going to help you in answering the questions. Right. So we go to the questions. And as usual, I encourage you to go through the map information, read through the map information and understand, because there might be some questions which require you to refer back to the map information, because that is where you get details about the mapped area in terms of its location, where is it located in South Africa, in which province, and also activities that happen in that particular area, its situation in relation to other features, and also some routes linking to it, be it railway lines or be it roads that pass through the mapped area. all those that information is very important. The climatic conditions of the area, you can also get it there, such that you are able to apply whatever you get in the map information if there is a question requiring you to refer to map information. Right. Then the first question is saying, in which province is Stress Town located? That is an application question which comes from the map information, basically, which means it's very vital for you to also go through the map information like what I was advising. So it's just going to the map information where you are supposed to extract the information in regard to the location of that particular. So if you check, our is in the Western Cape, according to the map information, which is response number C. The scale of the orthophoto map, we must always know that the scale of the orthophoto map is 1:10,000. The orthophoto is always drawn to the scale of 1:10,000. So how do we convert 1:10,000 to a word scale? If we want to convert this scale 1:10,000, it means 1 centimeter is to 10,000 centimeters. So if you want to convert this to meters, to use a word scale, so that we say 1 centimeter represents, because remember the word scale, it allows us to use different units of measurement, but on a ratio scale, it means whatever unit is here is the same unit on the denominator. So it's the same units of measurement. You cannot express numbers as a ratio if they have different units of measurement. We can only do that on a word scale. 1 centimeter represents how many meters here? For us to change 10,000 centimeters into meters, we have to divide by the number of meters, centimeters in a meter. A centimeter has got 100, a meter has got 100 centimeters. So we divide by the number of centimeters in a meter, which gives us 1 centimeter represents 100 meters. So using that, our response is A. Right, then the question now 3.1.3, it says refer to the topographic map, use information below to calculate magnetic declination for 2024. What are you supposed to do there? There is provided information on the map which talks about the angle of declination in the given year on which the map was drawn. If you check just below the topographic map, that information is presented in between the topographic map and the reference or the key. You get information about the angle of declination and the year when the angle was discovered, and also you get the mean annual change in the direction. You use that information to come out with calculation of magnetic declination for the given year. Let's use this as an example. Let's say our mean annual change is maybe 2 minutes to the west. So if our mean annual change is 2 minutes to the west, we are saying we want to calculate the magnetic declination for the map for 2024. Right. So we are saying it's 2 minutes to the west, let's say as an example. So we are saying difference in years is 10, which is we receive from the map information is for 2014, and we want to calculate for 2024, which means you are saying 2024, which is the year in question, minus the map year, we get 10 years, which means over the 10 years, over from 2024, the angle which was there had changed for 10 years. From 2014 to 2024, we now have 10 years, which means the angle of declination was changing further to the west for 10 years. So for us to get the total change, this is the average annual change. For every year, it was changing by 2 minutes to the west as an example. For us to get total change, we are now saying 10 times the 2 minutes to the west. It gives us 10 times 2 minutes, it gives us 20 minutes. So when you are now getting magnetic declination for 2024, you are now saying the angle which was there, let's say, for example, in 2014, on the map information, maybe the angle was maybe 25 5 degrees 40 minutes, like this. You are now adding the total change. From 2014, it was 25 degrees 40 minutes. But from 2014 to 2024, it has further changed by 20 minutes to the west. We add the 20 minutes, which give us 25 degrees. We add the minutes on their own. 40 plus 20, they give us 60 minutes. We understand 60 minutes is equal to 1 degree. So if it's 1 degree, we subtract 60, we remain with 0, 0, and the degree value goes to this side, which means it will be 26 degrees and without the minute value. Just using as an example how you calculate. What is the purpose of calculating the magnetic declination for the current year? In other words, we are saying, why do we have to trouble ourselves calculating the mean magnetic declination of the current year? It is going to help us to determine the position. For us to be able to figure out positions, we must be able to use the current year. We must calculate the declination for the current year, because if we use the previous year, it means we might not be able to locate places exactly. So we might be able to determine the position of features and the location of features and to navigate correctly by figuring out the magnetic declination for the current year. We need to use the current year for us to be able to locate positions correctly, or for us to navigate correctly, because the position of the magnetic north is always changing in that manner. So that is basically the idea. Calculate the actual distance of line F in meters between spot height. You just have to use your ruler and you calculate by converting the map scale. Actual distance is equal to map distance times map scale. If your answer is required in meters and you are using a topographical map, for a topographical map, if you are calculate your map distance, you measure it, and you say your map distance on the ruler, multiply it by 500 meters. You would have converted 50,000 to meters directly. If it is on the orthophoto, get your map distance in centimeters from the ruler, multiply it by 100 meters. You get your answer directly in meters. So for a topographic map, the scale of 150,000, if you had to reduce it to meters, you multiply directly your measurement from the ruler by 500. It will give you the measurement, the real distance between the 2 points in meters by multiplied by 100 for a measurement extracted from a topographic map, and for a measurement from an orthophoto map multiplied by 100, that is going to give you the actual ground distance of that particular, between those two particular points. Right, we move on to the next question. Why does the feature appear larger on the orthophoto map than in the topographic map? The reason is an orthophoto is a large scale map compared to a topographic map. To be specific, we say orthophoto is 5 times larger than topographic. So the issue is about scale here. What makes objects look bigger on the orthophoto is about the scale. The orthophoto is a large scale map, which means items are enlarged 5 times more than how they look like how they appear on the topographic map. So whatever feature you see on the orthophoto map, try to compare it with the topographic map, you see that the feature will be magnified 5 times. It has been enlarged 5 times because the scale of the scale, 1:10,000 for the orthophoto map is 5 times bigger than 1:50,000 for the topographic map. So items on the features, geographical features on the orthophoto map, they appear 5 times bigger than on the topographic map. That's the reason. The feature at E in block K5, you don't have the map, you're supposed to look at that. In which cell is the tricellular model of global air circulation affects the climate of Greece? Right, when you're looking at the tricellular mode of global air circulation, we are trying to refer to the climatic regions of South Africa in relation to the global air circulation. We find that predominantly placed in South Africa, they fall into the feral cell. If you check the latitudes of South Africa and compare them with those circulation cells, you find that most of the places, they fall inside the feral cell. It's hardly towards the equatorial region, then the feral in the mid-latitude regions, and then the polar close to the polar regions, after the subpolar region going towards the polar region. So South Africa is predominantly inside the region of the mid-latitude regions, and it is affected by the feral cell. Right, give a reason for your answer. I have just explained that. We are saying if you check the latitude of South Africa, of Suez, according to the map information, the latitude values, they are in between 30 degrees to 60 degrees south. So this region is dominated by the feral cell. So that's the main reason they check the latitude of South Africa, of that place. In which general direction does the river block G5 flow? Right, I'm just giving you the clue that you use to check on the flow direction of a river. Right, if a river is like this, for example, right, then you see we have what we call the tributaries of the rivers. Mainly what happens with the major rivers and the drainage patterns for rivers here in most of the regions, they have that dendritic pattern, which is resembling a tree and its branches. So you check at this angle here, the acute angle. The acute angle points the rivers, they join at an acute angle. The tributaries join at an acute angle, and the acute angle, this angle here points towards where the river is starting from. So whenever you look at the angle at which the tributaries join the main river, remember that the tributaries here, if the acute angle is pointing towards the northeastern side, it means the river is going towards the south western side. So this river is going towards this direction here. We cannot have a river having to branch and have distributaries unless if it's feeding into its mouth, where we have the formation of the deltas. But in this instance, we are inland and we are still having the river flowing along its course. So you check the acute angle and see where the angle is facing. Wherever the angle is facing the acute angle of the joining of those smaller rivers into the main river, it resembles that the river is coming from that direction. And also check, for example, if you have a dam wall like this one here, right, we know that water accumulates before the dam wall. So if you're checking the dam wall, you mean that this river is going in this direction because of the dam wall. Where the dam wall faces, where the river is flowing towards, and water accumulates on the upper part of the dam wall. So if there's a wall like this, you figure out. Then you also check contour lines crossing the river. If contour lines are like this, as they are crossing the river, you see contour lines having this shape here as they cross the river. Where the contour lines point towards here, your contour lines don't cross the river straight like this. They have to bend as they cross the river. So where they bend towards is where the river is coming from. So it also tells us that this river is coming from this side and is going this side. That is another clue that you can use. And also you can check the indicators of height, like the contour values. If you see a higher value here and a lower value here for the contour line, it means this river is flowing in this direction. You cannot have a river flowing from a low-lying area going towards a high-lying area. Or maybe there's a road here and a bridge, you see there's a benchmark, and maybe there's another road here and there's another benchmark here. You check the value of the benchmark, you see this one is a higher value and this one is a smaller value. It means this river is coming from this area going to this area here. Right. Those are some of the indications that you can use to figure out the flow direction of a river, just as a clue towards how you can give a reason to sustain your idea of a choice of the flow direction of a river in question. Right. What type of mass movement could possibly take place along the arterial road in block F6? Unfortunately, we cannot figure out where that block is because of us not having the map. But if you check the area and you see that it's gently sloping, we are likely to have mass movements like those slow movement processes. But if it's steep sloping where there are contour lines which are very close to each other, we are most likely to have landforms, to have mass movement processes like rock falls in those areas. Then it says suggest how human activities contribute to mass movement mentioned in 3, 2, 4. How do humans contribute towards mass movements? For example, rock falls, humans can contribute towards removal of trees or deforestation. If they remove trees, they can facilitate rock falls, or when they do construction on steep sloping areas, it also facilitates the rocks to fall. And also, like heading cattle on steep slopes, the cattle, they will loosen the rocks, and those rocks are likely to fall. Right. Briefly define the concept buffering. We are on GIS question 3.3. When we're talking of buffering, we are looking at a demarcation. The concept buffering refers to demarcation of a geographical feature. Otherwise, you're saying putting a boundary. Demarcating or putting a boundary on a geographical feature, that is buffering. For example, along rivers, we can put buffer zones along the rivers to limit human activities on the river, or to limit construction or other activities which might harm the river. We might put a fence along the river, or might plant some trees along the river to mark a boundary, that is buffering. Is a map scale an example of attribute or spatial data? When you're looking at those two, spatial and attribute, you must be able to find out. When you're talking of spatial data, we're looking at data that is showing about the location of a feature in terms of coordinates. And attribute, this is descriptive data, data that describes. So when you're looking at scale of the map is attribute data. It's descriptive data. It gives us further detail about the geographical feature. The map is drawn according to the scale of 1:50,000, which is also 1 centimeter represents 500 meters. We are describing the map. Right. The statistics below refer to trace, and the percentage increase in the crime levels from 2015 to 2017. We can see those statistics. Name 2 ways in which this data could have been collected. How would we have collected data about crime? We can use information from police stations. The police have got data about crime. We will use them to collect the information from police stations. And also, we can do surveys, either through use of questionnaires to find out if people have been exposed to criminal activities, or we can do survey through interviews. We can use questionnaires, we can use interviews to get the data, that is survey. Or we can also refer to national crime statistics. Is secondary information which is already provided, which you can easily access. And also we can use the internet and refer to Google and to find out information about that. Right. Also, we can use the census. It can also assist us in finding information about crime. Right. Then the next question is saying, is the information in the table primary or secondary? Is it primary or secondary? This is presented information. It's secondary. It's secondary information, secondary. Explain the importance of these statistics to the community. How is it important for the community to know about the statistics of crime in the area? It can assist the community in identifying frequency of crime. We can know how frequently crime happens. Frequency of crime in the area, we can be able to determine the frequency of crime. And also, it can assist in implementing strategies or solutions towards curbing of criminal cases, to implement strategies of how to handle the criminal acts. Then it can assist insurance companies. They can also benefit from that in terms of validating the claims which are made against them by the insured people. And also it can assist in crime prevention. The more we get to know the nature of crime, the more we are able to come out with preventive measures. So basically, that's the idea. We are relating to how the crime statistics can assist the community of that given mapped area. Right, with that being said and done, I think that is bringing us to the end of our discussion. And I hope this discussion is going to take you a long way in assisting you in preparing for the coming examinations. We are going to meet again in the coming discussions for paper 2, and we hope we are going to just assist each other and also map the way forward towards the best score. I understand the coming year is a year for metric, and we hope we have everyone on the train, we have everyone on board, and life goes on as per plan. Till we meet again in other discussions, your host in Geograph. Thank you for watching.